Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another lecture for intermediate algebra. This lecture is delving further into polynomials, specifically solving quadratic equations. And we're going to do in this lecture solving quadratic equations by factoring. So if you need a review on factoring, please refer to one of my prerequisite videos in the algebra material. I have them listed in playlists, and so I should have a few lectures in there on products and factoring polynomials. The first thing we're going to do, this lecture is going to be split into two videos. One's going to just cover the basics, how to solve a quadratic equation using factoring. And then the second part of the video is going to be focused on the more advanced stuff, the applications, that type of thing. Before we begin into examples, I just have to state a pretty easy theorem. It's called the zero-factor principle. Some people call it the zero-factor property. But it all just comes down to the basic fact that when you multiply two objects and their product becomes zero, then you know that one of those objects had to have been zero to begin with. So you multiply two numbers, comes out to be zero, you know one or the second number has to be zero. We're going to use this fact to help us solve quadratic equations. In fact, let's go ahead and just take a look at a simple example here. Let's go ahead and solve the quantity x minus 7 times the quantity 3x plus 2 is equal to 0. Now, this is essentially two objects multiplying to become 0. So that means either the first object is 0 or the second object is 0. So that implies that either of those two situations are true. Solve these two equations separately. So add 7 to both sides on the leftmost equation. Subtract 2 and divide by 3 in the rightmost equation. And we find out that the solution to this equation is either x equals 7 or x equals a negative 2/3. And you can actually check this. You will see that it actually does work. Now, often you're not given a quadratic equation that has already been factored. If you have, then you're very, very lucky. But in reality, most of the time, equations are not given to you factored. And by the way, that's why factoring is so huge, is because if somebody hands you a factored equation, they've given you all the work pretty much done for you. For example, this equation here. So I'm going to list out a bunch of examples, but this is just part A in this group of basic examples. 3y squared minus 6y is equal to a negative 3. Something you should probably notice is that there are two versions of y here. One being a y squared and one being a y by itself. In this case, or in all cases where you're given an equation, I don't care what the equation actually looks like, if you're given an equation that has two different versions of your variable, then you have to rely on special techniques to solve that. If you only had one version of your variable, for example, like a 3y minus 3 is equal to 5y plus 2, that only has one version. It has just a y to the first power. I can move things around and isolate y and I'd be fine. Same thing if you had something like 6z squared minus 4 is equal to 5z squared plus 10 or something like that. There's only one version of z here. It's just a squared version of z, and so we could easily solve that equation. But when you have two different powered versions of your variable, you have to rely on special techniques to solve. In this case, we're going to rely upon factoring. Now, one thing I have to tell you, the zero-factor principle or zero-factor property says that you have to have two things multiplying to equal 0, not negative 3. So do not just think you can factor the left-hand side to get, let me write this out as a wrong idea. Do not think that you could just factor the left-hand side. Oh, they both have 3y in common. Y minus 2 equals negative 3. This does not mean that 3y is equal to negative 3 or y minus 2 is equal to a negative. It doesn't mean that at all. So 3y does not equal to a negative 3, and y minus 2 does not equal to a negative 3. It's because we're not using the zero factor principle. There's a lot of ways two numbers can multiply to become a negative 3. For example, 1 times the negative 3, okay, that works. Or how about this? 6 times a negative 1/2. So you see, I've already shown you that there's two different possibilities for numbers that multiply to become a negative 3. There's actually an infinite possibility of numbers. However, if the right hand side was 0, there's only a couple possibilities. Either the first factor is 0 or the second factor is 0. It's just super important. I see so many students that immediately factor the left hand side without thinking. So if you have two different powered versions of your variable, move everything to one side. So in other words, add 3 to both sides. I'll do that in purple here. And when you add 3 to both sides, you have this nice beautiful 3y squared minus 6y plus 3 is equal to 0. And now I can start factoring. Notice that each of these three terms has something in common. They're all divisible by 3, so I'll factor out a 3. 3y squared minus 2y plus 1 is equal to 0. And now I can factor that trinomial. That's an easily factorable trinomial. That's just y minus 1 times y minus 1. So this tells me that either y minus 1 is 0 or this other y minus 1 is 0. Now, in reality, that means there's only one solution, right? So let me write either y minus 1 is equal to 0 or, well, the same thing. The second thing has to equal 0. But you see they're the same picture, so in either case, y is equal to 1. That will be our solution set. Some people might argue and say, wait a second, what happens with that 3? Why didn't you consider that 3? Well, really, if you have 3 things multiplying to become 0, honestly, either the first thing is 0 or the second thing is 0 or the third thing is 0, right? In fact, if you have a million things multiplying to become 0, one of those million things has to be 0 at least. Well, in this case, I could have written it out that or 3 has to equal 0, but in reality, when is 3 equal to 0? Never. So that's not a possibility. So we can skip out on that. Some instructors tell you to divide both sides by 3. It's not very helpful. It's an extra step. It's not super helpful. So the solution to this, there's only one solution. It's y equals 0. Now to introduce this idea, by the way, for later on in mathematics, there's an idea that we can kind of introduce right now that's called multiplicity. In other words, this is a solution to this equation, and because this solution occurred twice, it might be nice to write down that it has multiplicity too. In other words, that the solution occurred twice. It's not very useful right now. It won't be useful for quite some time, but just to let you know, some people start teaching it this early, just saying, hey, listen, you got that solution, y equals 1, occurred twice, didn't it? So I'm going to say that solution has a multiplicity too. You have no clue what that means at this point, and there's really no use for it at this point, but I thought I'd introduce it. Now here's our second example in our solution solving quadratic equations. This doesn't look quadratic at first, but we'll follow the order of operations. We'll clean up both sides here. So that t times t makes it quadratic, right? It becomes a t squared. And we'll distribute this 2 as well. So I'll get t squared minus 3t should equal 2t minus 6. I see that I have two different versions of my variable. I have two different powered versions of my variable. I have a t and then a t squared. Once I see that, I know I have to move everything to one side and do special techniques like factoring. So I'm going to move everything to the left-hand side. That means I'm going to subtract 2t from both sides, so I'll get a negative 5t, and I'll add 6 to both sides. And in this case, I can't say anything yet until I factor it, so let's go ahead and factor this trinomial. It factors nicely to t minus 2 times t minus 3. Those are two numbers that multiply to a positive 6 and add to a negative 5. So I have a number times a number, or an object times an object is equal to 0, means either the first object is 0 or that second object is 0. Solve both these equations, you get that t is equal to 2 or t is equal to 3. And again, you should probably check your work. Now, as an aside, for advanced students, if you're into pattern recognition, this is a really cool idea. I noticed one thing about these two objects. It's like t times a picture equals 2 times the same picture. Notice these two pictures. Let me highlight them. This t minus 3 is the same thing as this t minus 3. So if you were the type of student that likes patterns, you might go, listen, I'm going to subtract that 2 times that picture from both sides. In other words, I'm going to move that 2 times t minus 3 over to the left-hand side, and I'll get something like this. And notice in this picture now, so all I did is subtract 2 times t minus 3 from both sides. Notice in this picture, each of these terms has a t minus 3 in common. So I can pull that t minus 3 out front, and I'm left with, well, on the first term, a t minus, and on the second term, I'm left with a 2. And notice that I get the same factorization. And of course, two objects multiplying to become 0 means that the first object is 0 or the second object is 0. So notice that's kind of a very neat way to do that problem. But also, it's one of those things that I don't want a student to do mathematics this way until they're good with mathematics. Once you're good with mathematics, start looking for these patterns. Start looking for things that are kind of neat or kind of surprise you that you can figure out. But initially, you should just do what's written in green there, which is what you've always done. Distribute through parentheses first, combine like terms. You see that you have two different powered versions of your variable, which means you can't just, isolate a t. You have to move everything to both sides, or to one side, and then factor. That will be the tactic that you're going to use for the rest of your course in intermediate algebra until you get really comfortable with this idea. And you might start doing this aside, seeing stuff like this pop up. If you do start seeing it, then good for you. If you start kind of getting really good and doing stuff like that, because that means you're really showing mathematical maturity. So our next example will be a little more complex. As always, we try to beef up the examples as we move along. I will do the same idea that I did over on the example B, which is I'll clean up both sides by distributing to get rid of parentheses. So let me do this in red. So I'll take this z and distribute it to the 3z and also to the 2. So I'll get 3z squared plus 2z equals, and on the right hand side I want you to always write this out as z plus 2 times z plus 2. Students often, this is a cardinal sin, students often do this really stupid mistake where they say, oh, if I have a z plus 2 squared, that'll equal z squared plus 4. It's a very bad mistake. It's not equal to z squared plus 4. You cannot distribute this 2, this power of 2, into a parenthesis. Addition and subtraction are two of the worst operations in mathematics, in the sense that what you want to be true with them is rarely true. I would love it if this was z squared plus 2 squared. I would love that. So therefore it can't be true. Same thing for this. The square root of 9 plus 16 is not equal to the square root of 9 plus the square root of 16. I would love it if it were that. So therefore it's probably not true. Okay. Addition and subtraction have these properties that that you there's a lot of things you can't do with them. By the way, if you want to see why that second inequality is true, is because what's 9 plus 16? 25. What's the square root of 25? 5. What's the square root of 9? 3. What's the square root of 16? It's 4. That's going to be 7. So obviously 5 is not equal to 7. So obviously we did something bad when we broke that apart. You cannot split amongst addition or subtraction. All right, back to the original example. Sorry for that aside, but the fact is that it's super important for you to realize that. So a square, when you square something, it means take that object and multiply it by itself. So I'll distribute this z to each of those two terms, and I'll distribute the 2 to each of those two terms as well. So I get the following: 3z squared plus 2z is equal to z times z is a z squared, z times 2 is a positive 2z, 2 times z is another 2z, and finally 2 times 2 is a positive 4. Combine like terms, so I have a 3z squared plus 2z, which are not like terms, is equal to a z squared plus 4z plus 4. I see I have two different powered versions of z here, so that means I'm going to move things to either the left-hand side or the right-hand side, my choice. And I'm going to choose to move things to the left-hand side because I like my coefficient of z squared to remain positive. So I'm going to go ahead and subtract z squared from both sides, 4z from both sides, and 4 from both sides. I get this beautiful trinomial that I can actually factor a 2 out of. So let's see if this factors here, and it actually does. To 2 times z minus 2 times z plus 1 is equal to 0. So this means that either 2 is equal to 0, right? We have three objects, multiply and be equal to 0, so either the first object is equal to 0, which is not possible, or the second object is equal to 0, or the third object is equal to 0. This implies that z is either equal to 2 or z is equal to a negative 1. And those are my solutions. I'll just box those up. You can check those by plugging them back into the original equation. You'll find out that it actually does, both of those actually do work. Now take a look at this next example. This is a style of example that most students get tripped up on because they think that the left-hand side is factored, so therefore v plus 2 is equal to 8 or v minus 5 is equal to 8. But remember, you cannot do that. So just, I'll write it in red, this does not imply that v plus 2 is equal to 8 or v minus 5 is equal to 8. Because the fact is, if you're saying that, you're essentially saying that, well, either this first object has to be 8 or the second object has to be 8. The fact is, neither of them have to be 8. This one could be 2 and this one could be 4. Or this one could be 16 and this one could be 1/2, right? So there's a lot of ways to multiply two numbers to become 8. It doesn't have to be 1 and 8. So we have to use the zero factor principle here. So what we're going to do is go ahead and clean up the left-hand side by distributing the v's, or I'm sorry, distributing the binomial here. So v times v and v times a negative 5, 2 times v and 2 times a negative 5. So we'll go ahead and do that. Gives us v squared minus 5v plus 2v minus 10 is equal to 8. I see that I have two different versions of my variables, so I already know that I'm going to move everything to the left-hand side. So it's v squared minus 3v minus 18 is equal to 0. And now I'll try to factor this out. Two numbers that multiply to a negative 18 and add to a negative 3 are negative 6 and positive 3. And so two objects multiplying to become 0 means that either the first object is 0 or the second object is 0. Or in other words, v is equal to a negative 3 or v is equal to 6. Now, as a final example in this section, I want to bring up something about graphs here. Find the x-intercepts of the graph of y equals x squared plus 5x plus 6. I don't actually have to graph this. You just have to understand what an x-intercept is. Remember, the x-intercepts occur when y is equal to 0. A very easy way to remember that is just to draw any graph you want and think about these x-intercepts where it runs into, where your graph runs into the horizontal axis, and ask yourself, what do these points have in common? I mean, definitely not their x values. This could be like x equals 5, right? And this could be x equals 1. Oops, I already kind of gave it away. And this last one could be like x equals a negative 3. But their y values all have to be 0. So that's kind of the big hint there, is that to find the x-intercepts, you let y equal 0. So we're just going to say let y equal 0. If you do that, get this quadratic equation in one variable here, but just two different versions of it. And so I see I have two different versions of x. I need to factor that. That's what that means. So this implies that 0 is equal to x plus 3 times x plus 2. I just chose the easiest polynomial to factor, really. And so this implies that x plus 3 is 0 or x plus 2 is 0. Or in other words, x is equal to a negative 3 or x is equal to a negative 2. By the way, I'm going to erase this graph now so that people don't think that that's the graph of this polynomial. So this tells me that the x-intercepts are at negative 3, 0 and negative 2, 0. Remember, when you write the intercept for the graph of an equation, it's a point, negative 3, 0 and negative 2, 0. Often, instructors will accept negative 3 and negative 2, though. I'm just letting you know. Some people might be rigid or strict about that, but most people aren't.